Um, I think according to the schedule, we are supposed to do some conceptual design tutorial. We don't have access, not everybody has access to the handbook. So I want to just revisit some of the topics, and I want you to start doing something on your own in terms of thinking about what we are doing. I just want to make sure that you are following. I think I talked to some of you, there's some confusion. I've also got some questions. So what I want to do is I want to just start from the cast in place all the way to what I call it control rocking. See if you can get a better idea. So you can talk to each other, whoever's sitting next to you, try to figure out what would be the right response. I want to make sure you get a good feel for how what we are discussing here is making sense in terms of the behavioral. So most I'm concerned about making sure that you have a good understanding of how the system behaves. So let's assume it's a cantilever wall. Okay, so the first one is going to be a cast in place. What I want you to do is, so if it's a cast in place, you have foundation here. You will have reinforcement. Let's say, so you will have series of reinforcement. Don't worry too much about the plan view. All of this will assume that you have adequate longitudinal reinforcement. I want you to do two things. One is, if I'm applying load. So gravity load is something that we talked about, I think Satya also covered. When you apply the loads, gravity load is easier to transfer, relatively easier to transfer. Connections are not subjected to as much forces, and the details can be very simple. The lateral load is where we have been moving towards how will they differ in terms of precast versus the precast versus the cast in place option. So for this wall, if I keep increasing the force, or maybe it's easier to think as displacement, I want you to first sketch what the crack pattern is going to look like for this wall. We kind of discussed this, and I'm sure others also brought up this topic, but I want you to just talk to whoever's next to you and see if you can figure out what the crack pattern is going to look like. So the first one is a crack pattern. So assume that it's an adequately designed structure for flexure and shear. The second one is what you think the force versus displacement is going to look like. So this is displacement versus force. So I want to make sure that you understand, from a behavioral point of view, the cast in place versus emulative versus jointed. So three different terms we are using. We're kind of going to look at 4 different type of systems. When it comes to jointed, I want to break that into 2 other options as well. So you think, if you have done reinforced concrete, you should be able to do that, right?
Hopefully.
So you know what the bending moment is, very simple, right? The bending moment is going to be maximum at the base. So that's where the first crack is going to develop, right? So that's a good hint. So from there onwards, I want you to think about how the system is going to behave. So this is a cast in place option. When you get down to very simple things, I think it allows you to think through a little more about how the system will behave. So typically these walls will also be subjected to vertical loads due to gravity, so they may be subjected to gravity force as well. So you can assume the wall has some gravity load. But at some point, you're going to start seeing the first crack starting to show up somewhere here, right? That's where the maximum moment is, so that's where the flexural tensile stress is going to be exceeded, typically. Nobody's talking. I said you can talk.
Draw the pattern.
Yeah. I just want to keep it simple, but I want you to understand, because I want to show more videos related to walls. That's the reason I picked wall. I think some of you asked some questions yesterday during the break time. I felt like, okay, maybe you're not getting the whole picture. So this is going to make sure that, I think your question was about the jointed, what am I taking advantage of in the jointed system? I think this would hopefully help you. You guys are not talking. You have the answer? What's that? So I want you to draw the crack pattern on the wall if you keep increasing delta, and what would be the force displacement will look like.
Yeah, so this is the element. When you push, right, how the crack pattern. Over the crack pattern, you need to know the divide, right? So as you just like a cantilever, right? So how do you where crack? What number? Whether getting over this wall, right? So you draw the getting over diagram first, and then wherever getting over this higher. Then the next step would be how is it going to begin the load resistance section. That depends upon multiple factors. Right? Let's assume that it's a very bendy component weapon. Right?
Okay, so from a few very basic things you had to appreciate, right? So initially there won't be any crack develop. There won't be any crack, right? As you start pushing it, wherever the flexural tension go past the flexural tension capacity, your crack is going to start showing up. Up until then, you basically have the entire gross section participating or resisting the load, right? So you're from a force displacement point of view, you will have a stiffness which is typically based on the gross, moment of inertia of the wall, defining the flexural stiffness. The moment you start cracking the wall, it's going to start soften a little bit. So your stiffness change will take place from the moment you form the first flexural crack. As you keep pushing it, you're going to start seeing more and more cracks developing, right? Why do you think we develop more cracks? Yeah, so every time you exceed the flexural tensile strength at that section, the rebar doesn't get engaged until the crack develops. You design reinforced concrete with the reinforcement, basically to take the tension. They won't participate actively until the crack develops. Once the crack develops, there will be strain incompatibility, same as what we discussed for strain penetration, right? You have strain compatibility comes in, and then you start to see the flexural crack forming. So the crack will form depending on what stresses will, so typically you will find these spacing to be roughly the same, because the same rebar, same concrete, basically going through the same behavior, and your moment keep increasing. That means your flexural cracking moment migrate upwards, which causes the crack. You will also starting to see the shear cracks, or typically those ones will be the flexural crack starting to turn turn diagonally, basically indicating that the shear is also starting to play a part here. This area is where the full contact between the wall and the foundation, where the compression force is being transferred. Now, all of these behavior will be reflected in terms of how much force is being resisted, right? So if I go back to this, so I started with initially higher stiffness, the cracking develops, and then the stiffness changes. At some point, what's going to happen is that the critical region, which is right here, your steel is going to reach the yield strain of the reinforcement, right? As soon as your steel yields, your modulus of elasticity changes. When steel yields, it's starting to go into the curve path, which means the modulus at that location is going to be lower. So that's going to be reflected here. So if you have what they call a progressive yielding, so if I have a ward like that, this bar is going to yield first because that's the furthest from the neutral axis depth. The next bar is going to yield next. The third bar is going to yield as in the next step. So that means this curve is likely to be more of a curve because you are yielding multiple bars as you push through the different section, right? I've noticed that some of you draw the line horizontally, some of you think it's going to go further up here. Which one is correct? What's that?
Strain hardening.
Yeah, so rebars typically have strain hardening. So you know what strain hardening is, right? So if I look at the rebar behavior, they're elastic, then you'll have a yield plateau, and then you're going to go through this path. So typically you will find that this is your Fy, this is your Ey. Beyond this, the strength goes up. So typically, if this is Fy, this will be about 1.5 times roughly Fy. So it's gained quite a bit as it goes further into the elastic range. So if I extend this curve to the same ultimate point here, basically all of this is elastic strain, all of this is plastic strain. That's one way to think, right? So this increase, if the rebar carries, most of the rebar actually have the strain hardening behavior. There are some, I think it's called Temco steel in Europe. For some reason they produce them without strain hardening, which tend to be more flatter than what you see. There's advantage actually having, so the actual behavior, if there's no failure takes place, will follow path like that, and then somewhere it's going to fail. Right? So that's a cast in place. So think of this is what typically a behavior will be at the bottom of a column, at the bottom of a wall as we are looking at it, and then you could also look at a beam forming, moment resistant against the face of the column as we discussed yesterday.
What is the steel you mentioned, Europe, doctor?
Temco, I think. Temco, Temcore. Temco, I think it's the name of the steel.
Here we are getting about 20 to 30%.
Okay, 50, okay. So the grade 60, what we use in the US, that's 415 here.
Right, 450.
That tend to have about 50%. If you keep increasing it, then it goes down because they're basically manipulating the carbon content, which affect the behavior. Okay, so let's go back to now, let's take a look at a precast wall. It's not easy to draw something straight here, but it will. Okay, now let's take a precast wall similar to what we typically, so you will have a foundation which is built separately, or could be a precast element. You will bring and put it on top of a grout pad. I think Satya has shown some example of what they do in the precast industry. So that's basically your grout pad sitting here. The reinforcement that you put in the wall had to be terminated because so there will be some reinforcement in the wall panel. None of them will be going beyond outside of the bar, but maybe you incorporated some kind of a coupler or sleeves where the foundation bars comes in, and it splices with the so you have these couplers comes in, series of them. So all of these are, let's say something like that. So now we connected everything. Basically what we have done is we are forcing the wall to be comparable to the cast in place wall. So what I want you to do is the same thing. Draw a crack pattern if I keep pushing it with the displacement, and then look at what the force displacement is going to look like. So this is basically what we have been talking about as an emulation. We are emulating the rigid connection that cast in place uses. We couldn't use the continuous reinforcement, but instead we are introducing some form of couplers or sleeves to establish the full continuity so that I can create that behavior similar to the cast in place wall. So this is the emulation, as I said number of times, is to force the precast to behave like a cast in place structure. The question is, the detail is intended for that. The question is, does it behave in that manner? You know, again, we discussed this some already, but I want to see if you are appreciating the difference and if you recognize. So why is starting like this?
So you said since there are couplers here.
Okay. Where do you think the first crack will develop?
Somewhere.
Okay. Think about that. So when you put a coupler, basically, at that, over the length of the coupler, your steel area is higher now, right? So it's not, you increase the area effectiveness somehow, because you have, the couplers themselves are made out of steel as well. So they're not going to be same as the regular reinforcement that cast in place has. So if you look at the bending moment diagram for this one, it's the same as what you would expect. It's a simple, your moment is going to continue to increase. But the strain profile will not be the same because these area gets affected. You have more steel in there. So whatever the rebar in this area is going to see much smaller strain. But if you look at your movement is actually maximum at the base. I know several of you started putting cracks up here, but this area is going to be the highest moment. So, and you have, if you don't have any couplers crossing the foundation interface, then that area is very likely to develop the first crack. There are a few things to observe. It depends on what you use as a grout. So if you use regular grout, fiber reinforced grout, UHPC, those things would play in whether the crack develops within the grout element or within the concrete element. There's a natural interface here which has almost no strength at this interface. So this location, let me see if I can find, so somewhere here it could be at this location. So it could be, crack could be developing right here, it could be developing here, underneath the grout pad, depending on how cohesive the grout pad or the interface material is and how it's attached to. So sometimes they roughen the foundation and then the grout pad will stick to the foundation, it will develop above. Very unlikely you're going to tear the grout pad apart. They would use some kind of a fiber reinforcement in there. Typically it's a non-metallic to make sure the pad stays together. In fact, there was a group of researchers did some work on eliminating fibers in Japan, and then after doing a big test, they found out, oh, we should have included it, because if we don't put any fibers in it, that grout pad will get squeezed and then will start to disintegrate slowly, especially if you go back and forth with the earthquake type motions. So that particular region will see crack developing somewhere, but it'll be a little bit harder to predict in terms of where it would develop. So typically I've seen more likely in this region. Sometime you will find that for the reason I explained to you, that if I look at the wall panel, you get very soft interface at the bottom. So sometimes the crack develop right here. So don't try to prevent that crack from developing. It has to develop. If you try to, do some kind of a epoxy or roughen, it's not going to disappear. It's going to push that crack just above the base of the wall. So no matter what, you're going to have a crack develop. So the moment you develop your first crack, you will find that the stiffness will drop immediately. So up until then, it's a gross behavior. So force displacement wise, if I go back to this curve, the initial stiffness should be pretty similar. And sometimes you may, it doesn't have to exactly crack at the same load, because your crack flexural tensile strength may be slightly higher depending on material use. Sometimes it's lower if you don't roughen those surfaces. But it's going to start behaving very similar in the elastic part. There will be some small differences here and there, but I want to just go back and look at the crack patterns afterwards. So very unlikely you will see any crack developed in that region because of what we discussed, right? You have a chunk of steel sitting there, and you have to, so the reason is you're developing crack is you establish certain strain. That strain is going to be transferred to the reinforcing steel. In this part, your moment is still the same, but you got a lot more steel in there, so they're not going to experience same amount of tensile strain. Go ahead.
See, typically, whatever you put, it's a passive reinforcement. So it just opens up before the reinforcement kicks in. So
which one are you talking about?
The cracking will happen, but because you have plenty of steel, the crack cannot crop again.
You mean here you're talking about, in this region? Yeah. Yeah, I think even you guys did, I don't know if you remember what their test is also show. So yeah, like you may get some hairline crack. Yeah, but that region, yeah, exactly. So that region will essentially remain, at least it will show very unique behavior because you have stiffened that region with a lot more steel in it.
Like almost twice or thrice
Yeah.
the reinforcement.
And then you will have further crack develop in this region. Typically what happens is that if you go back, by the time you get up there, your crack width reduces. This crack width will be much, your crack width here is much wider than this crack width. So in these cases, these cracks are going to be pretty small, but this crack will tend to dominate, open up with larger crack for two reasons. One is all of this deformation has to happen somewhere, so it tend to happen here. We also talked about the strain penetration. In both cases, these bars will have the penetration effects, and therefore this crack will be a lot wider, which you can see it in all of your tests as well, right? There's a crack get wide open.
Is there any chance of sliding shear?
So it is a concern. So when you do details like that, you have to check to make sure that the adequate reinforcement is actually going through to prevent any sliding. In some cases, we have mechanically eliminated the shear sliding, but it's a possibility.
We talked about putting UHPC in the ground. I mean, anyway, it's crack, we got crack to happen there.
No, it will develop on the top of the UHPC layer. Yeah, you can't avoid that crack, no matter what you put in.
But maybe you can limit the crack to the service stage problem.
So say that again?
What's the intention of putting UHPC?
No, UHPC, but UHPC is also becoming so there has been argument over the years as to should we make that interface material more flexible than the member that's being connected to, right? So basically saying that your concrete strength of the wall should be higher than the whatever the interface is. I personally don't like the idea. So in the committee we had difference of opinions. At the end we decided that grout pad should be stronger. So specifically the ACI document calls for stronger grout pad than the member itself.
Maybe the compression side, because you push the strain ultimate strength so high, probably may not crush very easily. That's the only advantage I can think of.
Not so. See, the problem with the UHPC in seismic is that you take a regular concrete, you confine it, your strain goes up to much higher value, right? 10 times. So instead of 0.0035, you're at 0.03 or whatever number. You put a UHPC, the strain doesn't go up. But one advantage I see is that because of the interface, if it's a dynamic load, basically the member rock, so the impact, from an impact point of view, UHPC actually do much better. That impact is what damage and
performance, it's much
yeah. So for that reason, I think there's an advantage in doing it. So yeah, the dynamic load comes in, you begin to see some benefits. So you would have, there will be a drastic difference in terms of how the crack pattern develop. It also depends on how long is your coupler is, exactly where the coupler is located, and the moment gradient of the system. So in other words, the aspect ratio of the wall. All of that plays in. But I want you to remember that in each case, because the wall could potentially have different strengths, so we are evaluating all of the walls under displacement control, right? Meaning that we continue to increase the displacement so that the wall can fail at any time. But as you increase it, your moment gradient, moment is going to increase, and therefore the strain is going to increase, the penetration effect is going to increase, and all of that will be reflected. But as I mentioned last time, because you are concentrating the displacement here, your strain at this location will be pretty high because you have a very narrow band where large gap is opening up. So your strain hardening will take place lot more at the interface, and then therefore your penetration effect will also be relatively higher between the two. So if you go back here, this is what I said. As a result, because you have a higher strain, you will find that the wall would have, the wall would have, maybe you will see higher strength coming out, but it could potentially fail a little earlier than the cast in place. So they don't have to be identical, which is not necessarily a bad thing, but I want you to see the difference between the two and why. Right? So in some cases, your damage is going to look different, the behavior is going to be different. And then we talked about the fact that if you're looking at plastification, so you basically have, so go back to, so in one case, this is the maximum moment in cast in place. So this is the ultimate moment, let's say. Now you have slightly higher moment developed because of strain hardening. So you may get more shear into the wall as well, and therefore the shear can become critical. So especially if you have a short beam, short walls, the shear issue can kick in, and you have to account for that in the design properly.
Professor, can I show a detail which is adopted by our Indian precast?
Yeah, please. Yeah. You can draw here, or you can use a pen. Does it make sense?
See, in Indian precasting, what they do is, even like a company like Teenage, they will be having this sleeve, which is like a duct. There will be dowels sticking out
From the foundation.
from the foundation. This reinforcement and this may not match.
Yeah,
They
sure.
can be different. This is the type of thing they
Yeah.
do. That means they will be having a few dowels, which they will calculate based on maybe flexure, shear, and they will put this sleeves. They will lower this down.
Well, yeah.
But there is no, see, the way you showed is there's a
Mechanically connected, yeah.
between this reinforcement and this, here it cannot be like. Now, what do you think about this type of? I don't know, I mean, there is a lot of
Yeah.
stuff to understand the behavior.
But I thought it's all tied up.
No, yeah, you could have, if people have done it like, if it's a non-seismic.
My impression is, I think,
I've seen that like this, they do.
no, in ours we have checked, they're close, but there are other instances
Yeah.
represented that.
So what happens is when you put sleeves like that, they tend to put longer sleeves because
Yes, longer sleeves.
longer sleeves. So the longer sleeves would push the, almost eliminate these cracks developing. So your concentration, so in the New Zealand earthquake, this was very visible. They develop basically all of the cracks at the interface. And when you develop interface cracks completely at the interface, the strain buildup is faster. So when the strain buildup is faster, there's a lot of things happen. So this happens obviously in walls which were designed with minimum reinforcement. So there's not a lot of dowels going through. Once you have large strain develop at the interface, their modulus also goes down because they have the inelastic strain. So they can easily shear or, laterally they don't have much strength. You have develop a crack and plus their modulus is lower. So they tended to go sideways. So there's a lot of slippage took place. So yeah, the length matters, The other thing is that when you do something like that with the walls, if they don't develop cracks as we are envisioning, should be okay. But if they have less number, then the lap issue will come in, right? If it starts to have any large compressive strain developing in that region, then you can dilate and spool off concrete pretty quickly. So that region itself might work.
The concern is also the quality of grouting.
Yeah, yeah.
It's
So
all based on grouted, not low couplers.
yeah.
And hence, how will the quality of ground
Matters, yeah.
indicates
Yeah.
later? That's the question.
First of all, the lab architecture itself has some issues,
Yeah, this is not lab. This is just like a towels placed
But
inside
they
the
were
wall.
actually supposed to be leaked, so that's why I'm saying that it close to the lab.
Because see, the number of bars in the wall is much more.
Yeah.
They cannot provide so many number of towels. It will be very difficult to lower it down and place it.
Yeah.
Hence, they reduce the number of towels. Then they say that the area of the total amount of steel, I will provide the same area, but they will be
Less number.
dumped at few locations.
Yeah.
For the convenience of lowering it down.
Yeah, so if they are primarily a bearing wall, gravity supported wall, then there's no reason to have too many reinforcement.
Right.
So obviously the minimum reinforcement governs. So that's what happened in New Zealand. So they will just drop the wall. These laps could be as long as these sleeves would be as long as like 1 meter.
Yes,
So there is no crack whatsoever except at the interface. Once that opens up, your minimum reinforcement theory goes away because you really don't have enough reinforcement at that because they yield.
so if you go to the precasting site, I have seen in Tibet factory.
Yeah, I think I've seen it, yeah.
Yeah, those pipes that they place, their sleeves, and the reinforcement, they're separate. They're not.
Yeah, because it eliminates the alignment issue in the precast plant, right? They put bunch of rebar and the only thing they have to do is the sleeves and then they connect the pieces together. Yeah, I've seen it in other places as well.
Sometimes even the location is not considered, even better cars.
Yeah, they will locally bend the bars to.
To go there.
Yeah, I know, I have a lot of pictures from our own conceptual.
Yeah, so that's what I keep telling, right? The reason we do precast is to improve quality, not bending bars in the field.
The towels, because to facilitate even transportation, they're bent. And the larger the diameter, the more you bend it off,
Right.
it fractures. And we were not sure what to do. We cannot reject so many elements.
Right. Anybody else? Any questions? Does it make sense, you guys? Good? All good?
Sir, I want to see the strain distribution if you use sleeve or moment length. How do you do it?
So say that again, if you,
Strain distribution.
along the rebar,
Sleeves or moment length. What would the change in the strain distribution?
so this, okay, so I mean, you can just look at that from so if you say this is your bending moment profile, if I look at the strain, so let's say this is where the sleeves comes in, it will be, so let's get rid of one of these ones. So it should be identical to this one up until the sleeves position, right? That's what we are trying to do. And theoretically, this should have gone somewhere here. Because this strain is controlled by the moment, it's to do with the moment itself, right? But within this region here, where the couplers are there, your strain will basically come down quickly. So there's going to be some development length, that's what we are putting the thing, and your value is pretty high, so it will go down to some lower values and then come up again. So your curvature, it's reflected by your strain profile. Curvature dictates what the displacement is. So if I'm targeting to reach the same displacement, I need to have higher curvature to match the same area. In other words, your strain has to be increased. But that means this area of strain will continue to increase compared to a cast in place. So the more restriction you put in, the more increase in localized strain that you're going to see. And more likely to you cause the early failure because you're straining that location more and more. So anytime you see a large crack, it's a concern because you're concentrating strains. The same applies to UHPC also, right? Localization, same problem, which I've been telling people for 5 years. People still don't agree with me. It's obvious when you do a test, localization develops, but even in UHPC, I see the penetration takes place on both sides, so that kind of helps. It doesn't snap right away, but it's something that we should be looking at in specific problem cases.
So, but then what you're advocating is always put the coupler in the foundation. It's always better.
Well, not necessarily. Well, because if you put the foundation, I think I have a set of slides, I'll show you. If you put the foundation, you're killing the strain penetration.
Oh, yeah.
Right? So it may be convenient sometimes, but it does affect the performance. But the wall crack distribution will be better by doing it. But the precasters then have to have the bar sticking out to go into the foundation, right? So you have to pick and choose which is going to be convenient. And I think grouting the couplers within the wall panel is easier by having an outlet and inlet than trying to reach the foundation. So there are advantages and disadvantages. We actually looked at putting it in foundation versus and in the wall panel. We did see some differences in the behavior, but it's an emulation option that whether you choose or not. So by forcing the precast wall to behave like a cast in place, we are achieving some kind of an equivalency in terms of detailing, but I want you to know that it does actually affect the wall behavior as well as the force displacement to some extent. That should be given consideration. I'm not saying one is bad or not. Okay, let me just move to the next option. So the whole purpose of this, what they call a truss technology or jointed connection, is to say that, okay, we have this interface, this is going to crack open no matter what. Why don't we just rely on the fact that let open the crack just at that location? So one simple option is to have the wall panel. So let's see if I can create the wall panel here again. So you will still have, and then you will have reinforcement inside. This is your foundation. So let's not put anything across, except that you know that there's some gravity load sitting here. What would happen if I just push on it with the displacement? Again, I want you to think about crack pattern and the force displacement. So there's nothing crossing, this wall panel is sitting here, it's got a vertical load on it. I just going to just keep pushing it with the displacement.
Can you please repeat the question?
What's that?
Can you please repeat the question?
So if the wall panel, if it's a precast wall panel, I put it with a continuity using some kind of a grout pad only. There's no reinforcement crossing between the two. But I want to push it with the displacement. There are some gravity loads on the wall. So my question is, what is the crack pattern and what's the force displacement going to look like? You can take your phone and try this, right? Don't break the phone.
Cracks will be at the bottom.
Yeah?
It will be sudden failure only because of
Yeah, okay, so draw that. They're busy talking.
from both the sides there will be cracks.
Well, we push only one direction, you will only develop crack here, right? It's going to be.
Just slide it.
So assume that you have enough resistance. That's a good thought. Yeah, good thought. Hey, this showed up.
Bars are not going inside.
Huh?
Bars are not going inside.
No bars. So how many of you thought of some kind of a force displacement response? So I had a very good question from him. He said, is it going to slide? Right? If you don't have enough resistance, wall can also slide in this case, right? So I want you to realize that if the shear can be a problem in these cases, we have adapted a couple of different details to avoid the shear. So shear is an important piece. One is to put the wall into a pocket somewhere. So the wall will be sitting inside the pocket to avoid the sliding behavior. So you can assume it's a details like that. The other details that we have used is if the wall is, so we will bring a rebar in the foundation. Maybe, you can evaluate how many rebars you need. This will go into a pocket, but this is not going to be grouted, or it's basically put in a sleeve, so there's no resistance. There's no bonding between the two. So the wall can lift up, but it cannot slide to avoid the shear failure. That's a good thought. So as you would imagine, so let's say we have enough shear resistance, then you would develop a crack at the interface, right? You all agree? That's an obvious location to develop crack. So the concept of jointed wall, basically to say, no matter what we do, it's going to develop a crack at the interface where the two elements are getting connected. So therefore, we should acknowledge and take advantage of it. So if I allow this crack to develop, so you basically have some vertical load, so have some pre-compression. And so the initial behavior, initially it's going to start behaving like that. Let's say this is your, the center of the vertical load. As you start pushing it, this is going to migrate towards the right side of the wall. Right? As the wall starts to rock, your center of gravity is starting to move. Your compression is going to be somewhere here. Once you go past that centroid, wall is going to tip, basically. Right? So this is what's known as the free rocking structure. So it's free to rock, but it has an instability problem. So you could, you may develop some response initially. The crack opens up. There will be actually some other form of inelasticity kicks in, or reduction in strength kicks in. That's because initially your neutral axis depth is the entire length. After you open the crack, your neutral axis depth gets smaller and smaller as it starts to rock towards one side. And as you continue to increase the displacement, then at some point it's just going to come down and completely fail, or you just lost the wall. So this concept where you take advantage of the interface, I will only develop crack here, that crack will continue to develop. There's no rebar crossing it, so I will not be creating any unnecessary tension or within the rebar. Premature failures not happen. But as soon as you reach the tipping point, it's going to just lose the strength. So this is basically what I would call free rocking structure. So from there, I could go to what's known as the control rocking. Same idea. So I have some kind of interface material, but now I put a post-tensioning rod here. So it's a foundation here. So there's a tendon goes in there and hold the walls together. And I make sure this is unbonded. Let's assume for now that's what we're going to do. It's held only at the end. So it's like putting a long rubber band made out of steel, right? Same as, so if I have something holding it in place, I push on it with the delta. It's going to do exact same thing, but it cannot never tip because you have a restoring force in the pre-stressing steel. Same thing happened, behavioral point of view. Your gap will open up here. Depending on, so this is control rocking. So the last two examples are non-emulative. We are not emulating, we are not looking at cast in place and say, hey, it does look like the cast in place, but we are allowing it to rock. Then we realize the rocking is pretty unstable unless I introduce some restraining forces into the system, and therefore I would do this post-tensioning to hold things back. Okay? So the number of things I want you to realize with the control rocking is that when the wall uplift, basically you're going to have a compressive force here plus the post-tensioning force, and you have a resultant compression. That's your lever arm, and that would give you the resultant moment. So I can actually match the behavior or resistance of a cast in place with a control rocking wall behavior. Right? Strength, I need to put more steel. They're not directly comparable. I don't take the steel and duplicate here. All I do is I look at the moment resistance. I need this much, so I'll figure out how much post-tension to put in, and therefore I can get the same strength. Now, can I do this with the rebar? Can I do like a regular reinforcement instead of post-tensioning?
Ultimately.
Yeah, so potentially you could, but the rebar again has to be, so along that line I want you to recognize a couple of things. So this crack is going to open up. We have almost prevented any other crack developing in the wall panel. So all of the cracks, so if you're moving the structure to the same displacement, the summation of the crack that we looked at here, so the summation of all of the crack with will give you some number, let's say it's delta. The delta and this delta, how much it's going to open up, is going to be pretty similar. So all you have done is you push all of the crack to the interface. It's not something that you can do with a cast in place, and we are not trying to match the two together. We are developing, equivalent resistance in the two systems. I'm letting precast to behave like precast. I mentioned that, like with the UHVC also, some people are going to go back and force them to behave like cast in place. No, it's UHPC. So you have to figure out what the UHPC is going to do. So this crack will develop, so it could be pretty significant. You know, it could be as big as say 10, 12, 15 millimeter, depending on how big the displacement at the top is. So if I'm developing this delta here, if the strand or reinforcement there is bonded, then the steel at that location have to take that much strain, which is 10, 12 divided by, pick a number, something in the order of 100, 200 millimeter, your strain is going to be very high. So debonding the steel partially or fully has a significant advantage, because that way you can keep the strand elastic all the time. But the anchorage is a key piece which we discussed this. You could partially bond it. Go ahead, Satish.
Yeah, I mean, you just mentioned keeping the strand elastic all the time. But at the same point of time, this strand would also help in the moment resistance.
Yeah, of course, yeah. So keeping the strand elastic is not difficult if you keep the whole thing unbonded, because your strain gets distributed. So if you have a wall that is 5 meter tall, that 10 millimeter elongation is going to be distributed over 10 meter or 5 meter, whatever the number is. So you won't build up strain in the strand. So they will continue to act as like a rubber band. So you push on it, as soon as you let it go, because it's elastic, it's going to snap back.
Now, I have a question regarding the practical implementability. Now, this type of scheme, will it be used for one specific wall in a building as like a master wall, or will it be used in all the walls?
So typically what the precasters have done in the US is they would identify the walls responsible for resisting the seismic load. So depending on the load, they may pick, in one direction, okay, 4 walls have to do this. So then they will design them to be like this. The rest of the wall, if they end up putting it, they will be detailed to go for the right. So they modeled as a pin wall, similar to what we called as a free rocking structure. So they can rock, but they prevent the sliding taking place with some of the detail I mentioned.
So, I'm just going to raise an interesting question over here. Let's say, because the movement can happen both ways in the seismic or wind condition, let's say a seismic condition that we are speaking over here. So you have symmetrically placed unbonded strands,
Both sides.
closer to the
Ends, yeah.
of the wall. But the question was, in this case, when major cracks open at the bottom, then there is no real plastic hinge developing
correct.
In the wall itself. And so can tactile detailing then be eliminated in the wall?
Correct, yeah. Basically, yes. The answer is yes. So I think we ready for a tea break. So I just want to go through these 4. So I want you to realize that there's a cast in place option, there's an emulation option. In the non-emulative, we talked about free rocking, and now we're talking about control rocking. We've been talking about it here and there. I didn't feel like you have a good understanding. Hopefully it's much better now. And then we'll continue to show some examples and things like that after the break.
For the second one you said, sir, emulation.
Emulation, yeah. So in other words, so let's say if I have the wall panel, there are a number of ways you can do it. So let's say you put the coupler across here, across the interface, if possible. And so basically what their suggestion is to make this region very rigid and force everything to take place at the interface. So if the couplers cross the interface, obviously that crack is going to be very limited in terms of how big it's going to open up. So the crack, what you would expect, because if you increase the area of the steel effectively, the strain, corresponding strain, the moment is going to dictate in terms of what the strain is going to be. So the moment dictates the demand, but the area of steel will dictate what the exact strain is going to be. If you do something like that, all of your action will be shifted to somewhere here. right? When things get shifted here, you're trying to solve a problem, but you're also creating another set of problems. So typically, this region becomes more plastified. Because there was a question about what is plastic hinge. So plastic hinge is basically the length over which the plastic action is taking place, right? So it's not just, we call it hinge, but it happens over a range. So your plastic action is now shifted here. So if I look at the moment gradient of this system, so let's say this is the maximum moment that I would have developed with only rebar crossing, if this is the ultimate moment. Now the maximum moment is going to develop somewhere here. The shear problem again shows up. So you increase the moment, increase the moment gradient, therefore your shear demand corresponding to that will go up because your critical section is now here. So one of the other things that people have observed over the years is that when the plastification takes place against the foundation, which is a very rigid element, the plastic hinge development is much more stable. If that gets shifted, that plastic hinges become not as stable as when it forms against. It's to do with the confinement the foundation block provide. Because typically the tests are done in that fashion, that's how we develop everything. Now you shift it outside, the hinge is going to form away from the interface. So this region is not as stiff. So for example, spalling is going to take place. The buckling of reinforcements are more likely to happen, unlike what is something that you would see against the foundation block. So you definitely attract more problem even though you shifted the hinge. So there are advantages in terms of all you have done is you try to close the crack at the interface, but you move the problem somewhere else. No matter what you do, the crack has to open up in order to provide the resistance. So it's a matter of where it's going to be. So going back to the jointed concept is to acknowledge the best location to form is between the two members. That's where the jointed concept comes in. Allow that concentration of gap to open up at that interface. Right? Any other questions?
Also, this type of skin will unnecessarily stiffen it.
Yes.
And increase of stiffness means increase in size of
Forces, yeah.
which is not a desirable way.
Yeah. Okay. Let me see. A few other things that I wanted to share with you. So hopefully you have this knowledge, and we'll take a look at, I think yesterday I shown let's see if I open that. Yesterday I showed damage of structures from a couple of different earthquakes. I think the Northridge as well as some from New Zealand, Italy, I think. This is the same paper. That's not what I wanted to show you. There are too many things opened up. Let me close some of it. It doesn't like, we changed the resolution and it just getting confused when I change the file, so I'll put it back once I open it. So we've actually studied from a wall point of view, cast in place with no splice within the cast in place versus couplers and lap splices, so that we can see the differences. So even cast in place does the same thing. If you change the reinforcement detail with no splices versus couplers versus lap splices, it changed the behavior. And then also on the precast side, we looked at single wall, jointed wall, and then I also talked about pre-vec system. So then, given that pre-vec produced quite a improved responses, we studied that quite thoroughly. So I'll go through those things so you can understand. So most importantly, I think that we went through the behavioral thing in terms of how the structure behave. I want you to focus on how well these changes improve the behavior as well. So here's the 3 different walls was built and tested. So there are a few things I want you to observe and understand. One is this is a cast in place wall. The first one is a continuous bar. So the wall, basically the wall, the foundation bars continuously goes into the wall. In the second case, the couplers are located at the interface here. So, as I mentioned, it doesn't really matter whether it's a precast or cast in place. If you change the details, it's going to change the behavior. So that's the main point. Whether you bring that behavior through precast wall or cast in place is the same thing. So we decided to study this with the cast in place wall so that we can understand the behavior. The third one was lap splice, because this is a practice in the US that they will lap it. So the foundation bar will come up and then it will be lapped with the vertical reinforcement in the wall. So cast in place, this is permitted. But this is the region what we called as a plastic inch region. So the question is how much it gets modified. Again, I don't want you to just get hung up on details. But I wanted to get a feel for how things change when you change the rebar details. You could see these are rectangular walls, but we did have different details in each of the direction of loading, because we wanted to look at 2 different things, because the test was done to mimic a T-wall type behavior. So when you introduce couplers, you can see that you need to have sufficient room to accommodate couplers also. So it's putting couplers is not just a straightforward thing. You replace and put one in there. It causes some challenges as well. So this is, you can see in this one where the couplers were located, how the walls were designed and built. So clearly the couplers were located outside. So these are mechanical couplers where the bars comes in mechanically connect the pieces together between the 2, since it's a cast in place option. The test was done as shown here, pretty simple setup. Here's the wall panel. And you could see there are different zones because they are mimicking different flows. So the details were done as how you would be modeling or how it would be detailing a multi-story building. So that's the wall. It has a vertical load going through. I think we eliminated the vertical load for the most part. And then mostly our interest was to look at the plastification and resistance coming from each of the wall. So there was a question about what is plastic inch, how does it look like, and how bad this crack gets. Getting all interesting now. The questions are very, very detailed. So this one basically shows one of the wall tests. So this is what you would see typically. So you could see in this wall, see how the cracks develop. So the interface crack develops, the the load is going back and forth. The structure is getting pushed and pulled in both directions. So this is a video, but it's pretty slow. So let me, yeah, if you could turn, that would be good. Hopefully you can see.
The switches are on.
So when we say it's a plastification, basically you have inelastic strain developing. That portion of the wall that sees inelastic action basically causes damage to the wall. That's what you're seeing here. Okay, so I'm going to just move this a little further faster so you can see. So you can see how the crack is continue to open up. It gets wider. You're starting to see some spalling of concrete. Very small amount of concrete gets spalled off because those are cover concrete. So the entire region is what's known as the plastic inch region. Obviously the moments are high at the base, so the damage is going to be more. But when I say damage, it doesn't mean that the wall is losing strength. It can still resist the load. So this is providing adequate resistance. So you can see it's moved back and forth in each direction. Every time you move it to one direction, the cracks gets wider, so you can see now. So that's basically the plastification. So anytime the force resistance drops by 20%, we typically consider that to be a failed structure. So in this case, because of the hardening, you are continuing to improve, continuing to increase the resistance, but you could see, I want you to pay attention to the damage that takes place. So plastic action causes some damage, they are controlled damage, nonetheless it's a damage. So after an earthquake, typically you don't repair plastic inch because it's not easy or cost effective. They tend to take the structure down. So this is not a bad behavior in terms of what a cast-in place does. It provides resistance, but the damage is associated with it. So if you have a structure that goes through something like that, after the earthquake, people will not be allowing public to go inside because they will consider this as an unsafe structure. So you can see how it's disintegrating slowly. Okay, now you have this outer plane movement taking place because you have buckling, bars are going through inelastic action, they become softer in terms of its stiffness. So in other words, your modulus has dropped.
Sashi, I'm a bit curious, what is the instrumentation for that certain height? Is it for shear pressure?
Yeah, this set is so we broke it into 2 shear panels and measured that. Okay, so if you go and look at how the structure performs, it shows the progressive nature of the damage. So it starts so you could see the wall has moved 1%. I think the next one is 1.5%, 2%, 2.5%. So you can see in the 2.5%, you're starting to see more visible damage to the structure. By the time we end, so this is with the couplers in this case. So with the couplers, you could see there is a zone at the base, don't show any significant damage. More of that is going to be shifted up here as well as at the interface, which you don't quite see it. But you could see the number of large visible crack or damage that has caused is concentrated here, but more deformation comes from here, so this is where the strain penetration issue gets affected as well. So the example we looked at, emulation is going to look like this. So look at the extent of damage here. Now take a look at the wall without any splices. That's how it looks like. So this plastification is a lot more distributed. You're still going to have areas of concentration, so that's what you're seeing here. You can see the flexure crack, you can see the shear crack. So this is what we were trying to sketch in the very first place, right? So you've gone through that exercise, and then this gives you a different view. This is with the splice. When you have splice in the plastic hinge region, you can see it's a very different damage. So from a behavioral point of view, I want you to observe what you see here versus here versus here, and you cannot expect all three to be the same, even though we were trying to mimic all three to be, or we are trying to treat all three to be the same. So in the left splice case, basically the wall, the splice become weaker and the wall was failing sooner, and you can see the damage was concentrating due to the, typically what happens here is the dilation as the plastic hinge form would cause damage to the wall panel. So this wasn't the case in the previous two cases. When the coupler was put in, the behavior is different. So I think especially the students learning, try to focus on behavior. That will tell you how well the system will perform and not perform. So here is the one with splices. You can see 1%, 1.5%. Everything is concentrated at the base, not much. And then the failure of the splice eventually failed at 2%. When we reach the 2%, which wasn't the case previously. Now, if you look at the force displacement cycle, you could see that they are not quite identical. Certainly the RWS with the splice has lower resistance and failed a lot sooner. The other two has some resemblance, but you could see the RWC provided much fatter loop than the RWN. RWC is the one with the coupler. The reason it gets fatter is that because your strain concentration exercises more plastic action, which doesn't mean it's a good thing. It's not a bad thing, but you can potentially prematurely fail the rebar. But people misinterpret when they say higher strength, fatter loop is a good thing. But the premature failure can be a bad thing if you don't pay attention to that. Questions?
Why are the roofs not symmetric?
Yeah, because we had two different details.
Different types of
Details, yeah, exactly. So that was done to mimic a behavior like this. Right, so it's a T-wall, so we were trying to get the same behavior out of rectangle so that we can, so the question was, because the bar sizes changes and would that affect the behavior? And so we try to compare and contrast those things. This wall was also tested as a cast-in-place wall. Let's see how long this video is. I'll try to speed it up.
This is which lab?
So the test was done at the Mass Lab at the University of Minnesota. So it was easy to do the bidirectional test on the lab. And
How much each test would have cost?
what's that?
How much was the cost per testing each test roughly?
So this was come under, so I don't know if you guys know Professor Kathy French.
Yes.
So Kathy was my collaborator, so we channel money to both sides so that I get to test free. And then when we do the NEAST test was paid by NSF, so we don't have to pay for it. But things have changed now. Yeah, you can see how I want you to observe how much you can move these things while the system is pretty stable. So you could see again, it's a T-wall, which is common in buildings, and the damage is primarily happening at the base where the plastic action is taking place because it was tested as a cantilever. I think I probably have some pictures showing how so here's one direction. So again, I want you to observe what the plastification in a cast-in-place structure would look like. So they do behave well, but the extent of damage was pretty, the extent of damage associated with plastic hinging is pretty substantial. So when you cause failure damage like that, your cover concrete goes off, the longitudinal bars become, basically they get exposed, And in that case, they can buckle easily and fracture faster than if you don't have that, if you can prevent that from happening. So one of the things that we have done some UHPC testing is that the spalling doesn't happen because of the fibers. And when the spalling doesn't happen, the good thing is that the bars don't buckle. Bar stays together longer because there is no room to move around, right? So definitely they provide more ductility, but the compression strain capacity is a concern that causes some issues. So this is in one direction of testing. In the other direction, you could see the panel is, the flange is getting damaged. When you go in the flange direction, plastic inch foam on both sides, so you could see how much damage that is associated. So you take a precast wall now, even a double T concept, and try to model if you stiffen that one with a coupler where you're seeing the damage, then that damage has to go somewhere at the interface or outside. So the emulation, when we do, typically that's what we do. We are coming up with this detailed stuff. Typically in Japan, in the US, the use of couplers has become very frequent. It's became cheaper. I think it's probably the same here. The cost is not, so people tend to do couplers. It's not a bad thing, but it changes the behavior. That's something you should recognize in your analysis as well. This is the second wall we tested in the T structure, but let me just talk a little bit about the computer is not responding as fast as it should.
I think we need to appreciate the scale of the testing. So that is it. Industrial Minnesota.
So even I think it's a lab scale test, but they've done so well.
They had these platforms to monitor the cracks. You saw the students going up.
The resolution of the two systems is just spinning back and forth. Okay, let's see if I can talk a little bit about. So I want to just continue from the rectangular wall test we did. So there are three walls we talked about. Let's see if that picks up. So the cast in place with a continuous reinforcement was used as a regular reference wall for the precast equivalent of the jointed system. So this is what the controlled rocking is going to look like, right? So we said it has a recentering capability. So that comes from the fact that you have a restoring force in the system. So if you look at the controlled rocking, we put the post tensioning in the middle. If I push on it and let it go, the post tensioning is going to pull it back. So it tends to come back to zero displacement. You have minimal damage if I allow it to rock at the interface. You can take advantage of several precast technology benefits as well. The main question is the energy dissipation. How do we dissipate energy? So you have looked at some of these yesterday, what the press did and then what we did as a pre-vec system. So the main benefit of the pre-vec is that we introduced these couplers. And then I mentioned that by doing, if you're interested in matching the responses, you have to take the resistance from the cast in place, you have to design the appropriate amount of post-tensioning to match the resistance. So what you see here is, the red line is basically the response of the cast in place wall, which is the wall that I shown you without any splices in one direction of. So the reason we haven't shown both sides is that, like Professor Namala noted, that they had different strength, so we are only focusing on one side. You could see one of the pre-vec system that we designed is you can design to match. So this is a cast in place, this is a control rocking. So we said the initially stiffness will be similar, it tended to behave a little stronger or stiffer, but so there's no non-linearity takes place in the rocking wall. This happens because you change the neutral axis depth, and that's what's controlled this behavior. But the point I want you to make is that you can take a cast in place that you're doing, you want to do a jointed rocking structure, then I can look at the responses and I can match. And I'm not forcing this to behave like this, but I'm forcing it to provide the same resistance. That's what so we're not compromising on the stiffness or strength. The main question is, this provide a lot more energy dissipation based on the loop, hysteresis loop that you see. Can this be providing sufficient amount of energy dissipation? So that's the main concern that people initially brought up. You've seen these videos already. So I'll play this one again. So you've seen the rectangular wall response, and you could see, I don't know if it's a video or not, picture. Yeah, I think you've seen it yesterday, so I'll move on. I think it's taking time to load it. But no, I think it is running, but so when these walls respond, there's no crack develop, only opens up at the interface, right? The restoring force is provided by post-tensioning, and in this particular case, we added that O connector, which I will show you here in deformed shape. So you could see at 3% rift how this O connector is deformed now. So that is the one providing energy dissipation. I can increase the number of O connectors and get more energy dissipation out if I want it, or I can reduce it and provide less energy dissipation. And if you look at the two walls now side by side, that's how it looks like. So cast in place does its own thing, and the precast. So if I look at from a damage point of view, it's a night and day difference if I can promote the jointed concept. So in the examples that we did, basically I'm comparing the first example to the last example, but you can see they are similar in stiffness, similar in strength, but damage is different. So capacity design philosophy basically promote the idea of this plastification. So the idea is that if you have a major earthquake, your structure will get damaged. After the damage takes place, you take the structure down and rebuild it. So people never thought of that as a negative thing. But number of earthquakes, I think Kobe earthquakes, Northridge earthquake, it brought some critical structures down. When critical structures comes down, when they don't exist, it causes financial impact. And that becomes a big issue. So I'll give you an example. In the Northridge earthquake, there is one segment of a freeway system collapsed on I-10 in Los Angeles area. So that eliminated the traffic through that. Basically, that's a system goes through Los Angeles. And the city estimated that losing that structure cost them about $1 million each day. This is in '94, so maybe two.
How old was the structure, sir?
What's that?
How old was the structure?
So most of those structures were built in the 50s and 60s. So 94 is, you're looking at 30, 40-year-old structure. So the designers don't look at financial implication. We look at, we look at the structural performance. But the city complained that the design was not properly, and now we are losing $1 million a month, $1 million a day at that time. So they came up with the idea that they will put out a tender to rebuild their structure faster. I think they gave 3-month window, and then they said if you finish the structure early, for every day we give you $1 million, because that's the money that you're losing. But if you extend it beyond the 3 months, then you have to pay us $1 million a day. So the contractor took the job, put 3 crews to work on it, and they finished the structures obviously earlier than 3 months. But those things became, those things started to, imagine even here, right? You have, Delhi's the potential for earthquakes. So if you lose multiple structures in a financial building or key bridges, financial losses will be very significant. So the jointed concept actually help you to create structures that can be functional after the earthquake. So this is where the resilient design concept came about, right? So you make the structure to be more resilient. So if they are not damaged, like if you look at if you have a building with both walls on one building and one on the other, if you look at the one on the right, even a good structural engineer will be hesitant to go inside. Whereas one on the left is telling you, and you can inspect and evaluate and say, hey, did we have, because you don't want to have no damage but still in a bad shape. Those things we can easily evaluate. We can look at the post-engineering anchorage and things like that to make sure that system is still intact. So the concept of resilient, designing for resiliency became more hot after the Northridge earthquake in the US. And that's what kind of started the displacement-based design, performance-based design. So you design for certain performance depending on the type of structure that you're looking at. So if the structure is not critical, maybe you go for the solution on the right side. If it's critical, you do for left. What the precast industry wants to do is to show them any structure, we give you a solution cost effectively or cost comparatively with the cast in place option. So here is the test results from the pre-vec test that we did. The very first pre-vec test that was designed to match or exceed the response of the cast in place wall, and you could see how they can be designed to achieve. So it's a matter of figuring it out. There's not much to figure out. You need to figure out the amount of post-engineering, and then the compression zone can be sustained adequately. So this is what I keep saying, that you take advantage of the characteristic of precast and then let it behave the way it should behave to give you better benefits. So I mentioned that this concept has also been used in timber and steel. They behave the same manner as well, because there's no damage to take place. So even they have done extensive testing in New Zealand for timber structures, produced good results. There are some tests done in the US for steel structures. At Lehigh University, produced good results as well.
What is the relative benefit of this horizontal post-tensioning in the frames versus a vertical post-tensioning in the wall?
No, they behave in the same manner. The rocking in a beam, the bays are smaller relatively, right? So the gap opens up quite a bit. You had to account for it. In most of the cases, that the tendons will be running from one end to the other, because these are straight tendons, they're easier to pull through. So they still tackle that issue. But in the beams, they still use this hybrid concept with the rebar in it. So the damage, people have done some other mechanism. I don't know if it has been built anything, but wall definitely we have moved away from it. So this is a project in Japan. So the Japanese decided when the joiner concept came about, they wanted to see if they put two identical buildings on a shake table, they have a big table. So they, so they wanted to put both of them on the structure, subject them to the same earthquake, and see if the reinforced concrete and the precast, will they perform differently or they provide resistance adequately? Will they withstand this big shaking? So one on my right, so that will be this wall. This is a cast-in-place wall, cast-in-place frame, and so these are two buildings, 5 or 4 stories, and then you can see the gap between the buildings. So they are two separate structures. Let's see, is it going through? So you could see it's moving. So obviously both of them survived, right? Both buildings, stood on the table. You could see that the cast in place, you're starting to see the damage because of the plastification, whereas the rocking took place basically at the base of the wall. They designed this structure to be rocking with the walls going in this direction, but the rocking, for the other direction, it was frame structure, but still with the rocking concept. So this is another test. So one of the things they observed in this test was actually this hinge formed, and because of the hinge formation and significant amount of inelastic action, this wall was actually sliding at the base. So I know there was a concern about sliding, but this wall was not sliding, and you could see after a significant amount of testing, there's no damage to the entire structure. And the post-tensioning was designed to remain elastic even after subjecting to all these earthquake motions. They performed, they were undamaged, and then they obviously measured the residual displacement. So this was almost negligible. This one has a fairly significant amount of residual displacement as well. So you can kind of appreciate the benefit of going away from emulation concept and then trying to design this as a controlled rocking structures for precast.
Question, I mean, living in a real world, there are push from developers and architects and, significant changes happening during the design phase itself. Are there written design recommendations so that we don't have to go through detailed nonlinear analyses?
Yeah, so the design, ACI has, we incorporated this into the ACI.
Okay.
ACI has documents for both, so two systems. One is a hybrid frame. The other is I think they call it jointed wall system. I can get you the references. So there are documents that exist. It's been there for a while. ACI within the building code says that if it's a precast special moment frame or special wall structures, I think they call it, then they refer to those documents. So it's reference in the 318 now. So you are allowed to design in the US. So people have not designed much for completely different reasons. One is the owners don't see these slides or videos, whoever owns the building. So the moment you go and tell them about, hey, we can do an unbonded post-tensioning rocking, they said, is that going to be like that? And they say, no. Okay, let's do that, what we're doing. So that's one thing. So they don't have an appreciation for the advancement. Unless somebody understand and you promote that idea, right? The other main hassle is that it's something that I'm actually working on it now on the wind side. These are newer buildings and newer technology, and when they apply for insurance, the underwriters don't have a knowledge. So they ask the same question, is that going to be like that? And when they say, no, it's a new technology, then they ask, how many buildings out there? They know 3 or 5, as opposed to 100,000. Then they say, okay, we have to charge more insurance for those buildings because only 5 people are going to pay. So it should be the other way around. They should understand and give incentive. If you use this system, we'll actually reduce your insurance. That is a huge problem in many countries. In Europe, I see that there's a movement now towards getting the insurance industry engaged in the discussion, and so that they can recognize us, the underwriters have a better appreciation to incorporate these things. So I'm doing some work related to wind now with the insurance industry. And so they are saying that bring the policy, so the insurance industry, I don't know how that works here in India. There's a lot of regulatory bodies get involved. So they need to be, they have nothing to do with engineering or science, or, they're finance people, study, focus on policy development. So those people have to be educated. So to recognize and go that direction, it's a long road.
I think what will also help in terms of exposure is, a comparative design workshop.
Yeah.
Between a conceptual design and a normal case versus rock and roll design. I mean, one-to-one comparative.
Yeah. Yeah, those things exist. We are also upgrading codes, but we don't have any connection to the owners potentially, right? And they are like, when people say you will have plastification, coast damage on the building side, the owners don't even live there. Owners are in Hawaii or Paris or whatever, right?
But I think the owners can appreciate, although both buildings are safe in that situation.
Yeah, I think but
they would appreciate, more damage versus.
So in New Zealand, after the Christchurch earthquake, they had to take down quite a bit of structures for 2 reasons. One was they experienced some damage, but the insurance system, the insurance policies had a flaw on it. The owners felt like getting a replacement was a better option for the owner as opposed to repairing it, whatever the flaw they had. So they almost bankrupted the insurance industry. But because a lot of buildings came down, collectively owners were looking for what is out there that we should be using so that we don't run into the problem. So these systems actually have been used in New Zealand in the rebuilding of the Christchurch, city of Christchurch, basically. They use it in timber, they've used it in concrete. So if this had to happen in the US, multiple buildings were to come down in earthquakes, then there's potential, right? People will look for a new thing, like how people went away from masonry. It goes through the damage, and they realize, okay, they are brittle, there's not going to have issues. So it's an unfortunate situation, but that's a path that we've been going through. On the bridge sector, it's a very different world because the bridges are owned by the state, and they are accountable when there's a damage, injury, and all that stuff. So they are proactive. You tell them something. Again, they haven't gone to this far because they're saying, we haven't quite seen, we want to be careful, and they're still talking about it. I don't believe any other bridges have been built with this concept, either in high seismic region in the US. A lot of work has been done. They've seen enough tests, but anyway. Let's see if these things load up. I don't know why it's. So this is, I think this is what I wanted to show you in terms of the performance to concrete buildings in New Zealand. There are a couple of papers that I identified. Again, you know, I just want you to understand that so here's a column that's sitting on this corner here. I don't know if I can write it here. So this is a column here. Here's the flow slab. You can see there's a lot of de-stress took place in this region. You can see more here. So typically when beams and flow slabs are attached to the column, this plastification will elongate the members. So if the beams are elongating, that elongation has to be accommodated by the floor themselves. Typically we ignore them, but it is something that people have to account for. So one of the big push in the US was when they see this gap opening up, they will say, how is the floors going to accommodate? But as I explained to you, those gaps are not unique to precast. If you have cast in place, if you have steel structure, they're deforming. Gaps have to open up somewhere, right? Otherwise, you're going to, if it's a welded connection, it's going to just fracture. We've seen it in the earthquake as well. So the floor interaction has become more of a concern for precasters or precast structures. And then that's something you see here. This even before the earthquake in New Zealand in 2010, there had two events, 2010 and 2011. They took a more of a proactive approach, and they introduced this jointed wall concept in some buildings. So this particular structure has gone through earthquake. So just like what I showed in the press building, you can see the couplers. So these are the energy dissipating elements. These are individual walls connected together. Here's a close-up. This building actually went through the same earthquake in New Zealand and experienced very limited, very limited de-stress to the structure. The structure was not damaged, or people were able to occupy it. Whereas some of the other precast structures, I don't know if you can see, I'll point out some of the details. So you could see this is in this particular case, you could see damage happening at the beam end region here. And then this is supported on inverted T, on corbels, you could see the beam end region is experiencing damage. So these are the structures where emulation was used to connect the beams to the column. And whereas this is one of the structures that used the jointed concept and performed better compared to these ones. So the New Zealand earthquake did produce some useful results in terms of showing how well the jointed concept can perform. This may also have some pictures of New Zealand earthquake damage. So there's a section on precast building. So these are cast in place structures. Yeah, so here is a lap detail that was used in this particular structure. So you can see anytime you change the the continuity. So the lap splice comes in, and that's where the failure was found in this particular structure. These are older buildings. Yeah, if you are interested in these articles, I'm happy to share it with Virendra. Okay, so here's another floor details. You can see that every time you open up a gap for plastic hinge, that has to be accommodated in the floor as well. So the floor can be designed to be flexible, but if you don't, then that problem will show up. Let me go to a precast section. Okay, so this is all precast structure from this particular section onwards. You could see some settlement of the beam here. So there are vehicles. They're basically sitting on top of the vehicle, so they came down. This is a parking garage. We talked about the punching shear is a concern, so you could see the slab was here, basically punched through the column, so the column punched through the floor slab. This happened in the same structure as well. So when you do, so typically to create a pin details, they would use a rebar connecting or bolted connections. They typically use that for bottom of the columns to mimic a pin connection, as well as beam to column. So when you do concentrated, especially if you put multiple threaded rods or whatnot, people make an assumption that they all will be acting simultaneously, and it will not be the case. So when that happens, the pull-out elongation will happen. If it goes back and forth and corset, then it becomes a sliding problem. So the elongation of anchor rod was a very common thing. Yeah, this is an old structure that caused a lot of damage. So these are the two buildings that caused a lot of injuries and deaths. That's what the paper is talking about here. Staircase I mentioned, so it is common in the New Zealand to use precast staircases, very popular. Staircase themselves perform well, but the connections, again, the precast means that connection has to be robust, otherwise you're running into issues. Let me just go back and talk about a very different topic here. Okay, I want to go through more of some of the details that we built from this jointed concept. So this is, I think I mentioned the press program. So the press program produced multiple details, so two of which is the hybrid frame as well as the jointed wall concept. It was done in 3 phases. The first phase was a concept development. So basically people came up with different ideas. Emulation was one option they considered. But that's when this jointed concept was get pushed harder in terms of making it happen. So this happened back in the, I would say, early 90s. And then the second phase was done to understand the different connection concept people came up with. And the third phase basically did did the building test. I got involved in the third phase of the project, the press program. Then we developed guidelines and all that stuff. But some countries have more advanced. New Zealand has a press technology handbook, basically, to implement. ACI has documents for these two. So yeah, we don't have to do everything, reinvent, right? We can take this, run some analysis. I know Professor C.V.R. Murthy insists on testing. You could do some testing. You don't have to build a 5-story or building to put on a shake table. But some limited testing you can certainly push. But main thing for me is the PT's anchorage. And we also studied on the US some of the PT anchorage to make sure that, but those tests can be done fairly easily in the test labs, right? If you need a uniaxial machine, you guys even have the heavy uniaxial machine, you should be able to evaluate that fairly easily. So I think a plan needs to put together in terms of, this is what people have done, this is what we need to do to go to the next level. I think Siva Sidambaram can get involved. I think they have a capacity to do tests. So you just have to bring a coalition related to precast and what tests are needed. And again, you don't have to push all of the systems. I think a wall structure and maybe a hybrid frame is a good starting point. And then you can do fine tuning based on what's more attractive, what you think is appropriate for your crew to handle without concerns. So you could see they are obviously made from precast elements. Most of the deformation occurs in the connection, so very different from cast in place, which is deformation occurs within the member. We are now in the jointed concept, we are forcing the deformation in the connection. Member is largely protected from any damage, lower repair cost, shorter downtime after an earthquake. Connection must be provided with the needed properties. So basically, you can force everything to the connection, but then connection should be designed to do its own job. So the performance is in the precast system now is tied to the deformation capacity. So you have to have the deformation capacity, which should in turn open up the gaps or the deformation at the joint. The non-elastic connection can be used to increase damping, which I'll talk more and more maybe next week as well. In the phase 3, we basically wanted to bring in different technology together and test them using one building. So component testing is appreciated, but sometimes people wanted to build larger structure, and so precast industry was heavily involved in this particular project. So they were able to shell out money towards doing this testing. So because the large size at the time, US didn't have a large shake table, so we decided to do this test using pseudodynamic. So pseudodynamic is basically what now known as the hybrid testing pretty much, right? So this is how the structure was envisioned. So basically you would have 5 stories, and 3 stories will have one floor type, and then 2 stories will have different floor type. So the bottom 3 stories relied on double T floor, so each one is a double T floor running in this direction. And in this direction, the seismic resistance was provided by jointed wall. I've shown you some of the pictures, but that's sitting in the middle. These are gravity columns. So gravity columns are fine as long as they transfer the load, but they have to go for the ride without losing support or losing the base. So that should be accounted for. In the other direction, the seismic resistance was provided by these 2 frames, but all of this have to go for the ride, including the jointed wall in the outer plane direction. in the opposite direction or along that direction, the horizontal direction, if you like.
See, here the wall was not connected to the columns. That is, there was connection between the floors and the wall.
Board, yeah.
How
So,
is that connection?
yeah, I'll show you. The seismic load was transferred through the connection. So since then we've studied, because the flow became a big issue, so since then we studied how to rigidly connect and how to disengage the floor, but still transfer loads. I mean, there are devices people have come up with now, and all of that is possible. So this is the other floors on the top, which relies on hollow core panels. So you could see these are hollow core panels that was tested, and this is again the frame direction, and this is the wall direction. Okay, I don't want to spend some, so yeah, this is supposed to be about 60% of the actual scale. So this is what the elevation looked like in one side. So you could see one of the frame had this particular detail. I'll go into the details again so you can see how we can introduce different details. So you could see this is, the beam is continuous, but column is not. So these are where you would put in some grout pad to establish connection. So this is known as a pre-tension connection. And then here, the column is continuous, the beam is not. And then here the connection was established using hybrid concept. This is the other frame. This particular system was looked at. I'm not going to spend too much time, but they call a tension compression eel frame. That was used on one direction on the top two, and then these will have a slightly different details as well. For the wall system, you could see the post tensioning was done, basically anchored into the foundation. The entire wall was, the entire length of the post tensioning was unbonded. And that's where the U-plate connector was incorporated. The structure was also designed using a displacement-based design. I don't know, I think a lot of people disagree with me or would get upset with me, but displacement-based design kind of allow you to use large, R factors, basically. There's no way otherwise you can bring the force down. So it was done basically to show you can actually use a lower forces and still provide resistance adequately. So from a design point of view, I want you to just get a feel for these things. So we have a seismic frame, we have gravity frame, wall, connections in vertical structure. You have hollow core floors that need to be connected. You have double T. So you can see how you make the structure more complicated, but advantage is that in one structure you can test all of these details. So the jointed wall was designed in this fashion. So as I shown yesterday, as you rock back and forth, the wall will rock at the corners here, the post tensioning. So this is, each one is a jointed control system is what we're dealing with. And this element here is going to provide some energy dissipation so if you don't have any energy dissipation, what you will find is that the force displacement tend to be more, it will be more like, so this is your force and displacement. Because of the post tensioning, it will go up and then it will just come down here. So you won't have much energy dissipation inside. Whereas you saw that in the cast in place, you get energy dissipation that comes with it as the plastification takes place. So the connectors were put in so that this can open up and produce some kind of a additional energy dissipation on top of what the system can provide. So So there are some key issues in the jointed jointed system that you'll pay attention to. So you don't want the post tension to yield. We talked about the fact that once you yield, you have the potential to lose some or all of the post tensioning. So you want to keep the post tensioning, at least make sure that under design level you don't develop any yielding. When you mix it with the connector also provides, so when you put the connectors in the middle, then there's going to be moment resistance coming from the connector as well as the post tensioning. So you need to decide what percentage is going to be from post tensioning, what percentage. So if you get more from the connectors, then you may not recenter it. So that's something that you should, again, there's been a lot of work done on that topic. Yeah, so this basically explains the strength is going to come from yielding of the connectors and the PT, the post tensioning, and the residual drift will be dependent on how much each of the system will provide. Okay, so you can look at the structure now on all five stories. So you can see the structure has a lot of opening because we have you have frame in one direction, the wall is at the center of the structure, and but accommodate all of the different details. The connection between the wall was done with a U-plate, so we found that somebody investigated this back in the 70s as a potential energy dissipators. Because of the shape, we felt like this will do a better job, and it did do a good job. The reason in pre-veg we avoided that was, I think I mentioned yesterday, it's a cost issue. These are stainless steel because this U-plate rolls on the side of the wall quite a bit, so they go through a much larger strain. So if it's a regular steel, our concern was that you can fracture or you can damage the U-plate pretty quickly. So that was the reason they prefer to do that. Okay, so I talked about four different frames were used in the building. So I want you to understand how these things were envisioned. So this is continuous beam. So this is called the pre-tension frame. The beam was continuous, column was discontinuous. So each of the column is story height. They're connected with a grout pad here, and they had couplers here. So we kept talking about we don't want to use couplers, but in this case, it was designed to open at this interface. So if this is not a critical path for the energy dissipation, if you put couplers, then there's no harm in doing it. So the couplers were used to establish this connection. So what they envision is that if you displace laterally, that's how it's going to open up. So if you see, so basically your design should be such that the column should not be causing any yielding or any deformation here, but this is what known as a strong column, weak beam, where the beam is forced to behave.
Is this pre-tension or post?
Pre-tension. This is a pre-tension system. Because the beam was designed, the pre-tension was included in the precast factory, and the beam came as a one long piece. So precasters prefer that option. Again, if you go back to UHPC, if you're doing something detailed like that, can work really well because you can put pre-tensioning, can take a lot of compressive forces, right? So you can see some of the details I mentioned. So this is continuous, the beam is continuous, but the couplers were used to establish the connections. This is what I show as a hybrid frame where the column is continuous, but beam had basically a bay length. This is a post tensioning that was run from one end to the other to hold everything together. And this is they put mild steel reinforcement in the hybrid frame, and the purpose of that is to cause the energy dissipation that we are looking for. And again, if you push on it laterally, this is what's going to happen. This is what expected. You would have a gap opens up here and gap opens up, and column will remain undamaged and beam will remain undamaged except this gap opens up. So this gap will cause strain concentration in the rebar and therefore will fracture the bar prematurely. So to overcome that, as you can see here, this darker line indicates that portion of the bar was debonded. It's basically you put a duct tape and release it from bonding. By doing that, it allows the gap to open up and the strain to be distributed over a 150, 200 millimeter, which is something you can calculate. So the key is to realize that with the jointed system, so this is again a controlled rocking. The beam is going to rock in a controlled manner on the column. We talked about the wall, it's the same thing, right? So that's a hybrid connection. So this is a TCY, tension compression yielding frame. This didn't perform as well as we envisioned. Let's see. So I just don't want to spend too much time. Again, if you're interested, there are papers written on this. The concept is the same. Gap should open up. So in all of the cases in the jointed system, the goal is to force the gap to open up at the interface between the column and the wall. So this is a TCY gap. This may be worth exploring. So in this case, the unbonded post tensioning is actually located at the bottom. So when you displace it, it behaves like this. So this will continue to have the contact. So your post tensioning is done with the grout pad only over a portion of the depth of the beam on both sides. So that's why this force can be held. But this steel here on the top will provide the energy dissipation. So it's a very different concept. It did have some issues because I think one of the things that we ran into was that still this one, as it yielded, this zone become weaker and the beam sliding was become a concern. So that's something you need to be looking at it. So the design was done such a way that columns to sustain minimal damage, remain elastic, but accommodate beam growth. So any times you have rebar put in, so this is something people don't appreciate. So we talked about plastic hinging. Every time plastic hinge happens, basically the member grows in length or height, right? So that member growth is real because your strains in the rebars are increasing. They are going from very small elastic strain to much larger plastic strain. So basically wall will grow with time. So that has to be accounted for if you have a floor slab, if you have elongation. If you try to prevent the elongation, then it will create other problems to the structure. And there are some researchers studied this topic quite a bit about how to quantify the elongation, how to account for it. Again, it's nothing to do with the type of structures you look at it. So even in a cast and jointed system, the gap opens up, you can appreciate that means it has to elongate or it has to grow in height in order to accommodate it. So the structure will do this on its own, but if you have floor slab, imagine in a wall situation, the wall has to go with it. And I will cover that a little bit more on Monday. So create a pin connection for gravity columns. This is what we did. We basically took the gravity column. This was not necessary, but ran a post tensioning all the way at the center so that it will have small moment resistance, but it can do this elastic behavior, and it can also provide the pin support that we are looking for with a pretty reduced amount of moment resistance at the base. So the structure also tested all of these, basically frame connections, wall connections, and then floor connections, wall to floor and frame to floor connection behavior as well. All three aspects obviously have to be looked at, whether it's a cast and place, precast, jointed, the strength, deformation capacity, and the energy dissipation. In a cast and place, I think with the direction we went, everything was kind of integrated together, right? Because if you move it, the rebar has to yield. That provides the deformation capacity. Because of the plastification, you have energy dissipation taking place. Whereas in a jointed system like that, where we have control over what stiffness to design, what strength to design, it doesn't have energy dissipation, so I need to provide the energy dissipation. I need to control that. And then deformation capacity is also, we can control as to how much deformation is needed. So the advantage is that you separated everything in a jointed connection. The disadvantage, you have to basically quantify and integrate them so that structure will have enough energy dissipation capacity and things like that. So in cast and place, it's kind of came with it, and then we back calculated and talk about, okay, it can deform up to 3%. It can provide 30% energy dissipation. Those are all came with it because of the way we design. Now, we introduced monolithic or emulation concept. It's changing some of these things because you're changing the behavior. Now, from there, we went to the jointed concept. We are able to separate some of these things, but we need to match. We don't have to necessarily match everything exactly, but you need to quantify and say how much I need. So damping would be a good example. Okay, do I need to produce 20% damping? Can I do less? So in this particular case, the amount of U-plate we put in, I think the minimum amount of damping that we got was 18%. That's what ended up in the ACA code, because the committee in charge was comfortable throwing that number. So that's what we have. And I think the next revision, my goal is to try to reduce that number to maybe 12 to 15%. Again, it's a committee, I don't know how this works here, but it's not, when you change these numbers, even with proof, people don't necessarily buy it. So they need to be comfortable to accept changes as well. Yeah, I think I don't have the pictures of the connection, but I may be able to show some of the connections. So let's see, what's the time like now? Where's brain? It's 1 o'clock. So we take a break, and you're starting right after the break. So I'll continue some of these things. So think of the direction we are going. So on Monday, I will show you some jointed wall concept, more testing on the pre-vec, and then the floor interaction is the other important piece that we should be addressing. The jointed wall, the rocking, that's the other element. So if we have time, we can spend some time. So again, I don't want you to go darker in that space, but even if you're not doing for seismic, but getting exposed to these connections, you need to appreciate that. So for example, if you're doing in a non-seismic, you're doing a wall connection, you could easily put in an unbonded post-tensioning. You don't need anything else, just put some shear resistance. You should be good to go. But people won't be comfortable because they don't know testing. This has gone through extensive testing. Have seen that. Hopefully you're comfortable introducing this for non-seismic, and you can put in some minimal requirement. I'll show you the wall panels when the structures rock, typically have minimal reinforcement. There's nothing in it. So you save a lot of materials, a lot of those things anyway. All right, very good. Any questions, anybody? Or you ready for food?
After that, was there any, I know, photorealistic equivalent to that of stick-to-witness.
What's that?
But real stick-to-witness have been done.
Yeah, one of my students did some work recently in China. So China is now doing, Tongji has a table now. So they So they have studied this. I mean, I kind of lost interest a little bit because people are not implementing, right, to be able to push. So China is investing crazy right now in terms of building facilities. So they're trying to match or beat Japan and US in terms of sizes. So Tonji has built a large table. It's not as big as some of the ones exist. So they did some of these testing. And again, like we did a lot of tests. I don't know what else to learn there. They may have done some tweaking. They may have looked at some other things. They were also going to look at some kind of more of a building performance. I also have interest in using this Prevec system for a core wall system, so that if you bring in a core wall, how does the connector works in 3 dimensions, right? So or do we need to develop some new connections? So then you can introduce into the core wall, or even T-wall and things like that. So Rick Henry at University of Auckland, he worked with me on this project. So he is kind of interested in exploring this a little bit more. Yeah, the people, I mean, I get to review papers where people take one connector out, put a different connector. I mean, things like that is happening also, right? But yeah, I think if there's more interest from the industry, then we can do more. The industry thing is the slowing things down. I don't know if this will change with I think I mentioned that our NSF is going in a very different direction, but they have an economic impact. So some of the grants are small. You're looking at $300,000-$400,000. On the high end, if you have a concept, let's say UHPC, I thought about, can UHPC is something could go that direction. If you can bring industry together, it would be a 10-year program, and the program can invest up to $160 million over 10 years. But at the end of it, they want to see a big economic impact to a region. You can define what the region is. Region could be a city or 2 states or entire country. So like biotechnology folks are getting into it. In fact, we are on the shortlisted for a biotechnology. Iowa State is taking a lead. Energy side of things. But they are also pushing the industry to commit some money. So now what the expectation is that if NSF put in 160 million, then the industry need to put something in the order of 300 million. At least they need to commit. So now you have a $500 million investment potential over a 10-year period. So obviously the topic has to be broad and impactful, and then it can change the industry. But they don't give you the check 160 million day one. Yeah, they give you and then they evaluate and then say if you're making progress. So we do have like on the medical sector, biomedical is growing. There's some activities. Broadband network, that area is growing. AI. So where the potential partnership are more likely. The problem with the UHPC is that industry won't put in $300 million. That's what the problem is. Or civil engineering topic typically. If we have the industry, certainly we can go. Yeah, they're looking for making a change. So NSF has a new program for this actually, a pretty significant amount, but they're putting a lot of money in there. So it'll be interesting to see what happens in the next 5-10 years.
Yeah, thank you.
Very good.
We'll wait for lunch.